Then we'll do some extensions. And then finally, yeah, we'll just be sticking around talking about extensions for basically as long as you want. But the first section where we'll actually be doing the lecture and doing the Jupyter Notebook where you train your own DC GAN is about an hour, and we'll just stay around, and you guys can basically take this as sort of office hours.
Yeah, so feel free to ask questions in Zoom, and then we'll try to answer them between sections. Okay, so I guess I'll start off by jumping into some of the applications and seeing what GANs can do, just to kind of motivate and see why we want to like study more about this. So I guess probably the most common or the most well-known application for GANs is generating images. And I don't know how many of you are familiar with the website thispersondoesnotexist.com, but basically the person who created that website trained a GAN to basically generate new images of people's faces. So every time you refresh that website, you can just see new images that the model is creating, and I think that is like pretty impressive on its own. Feel free to go to that link and just try it out. There's actually a lot of other applications too. So this is actually another, using the same model as the previous website. There's this little interpolation loop that GANs are capable of doing, kind of interpolating between different people's faces. But GANs have been pretty much applied to do other interesting tasks, such as basically image super resolution. And basically that means taking an image that's very like low resolution and pixelated and trying to interpolate it and make it more high resolution. So the original image isn't shown here, I think, but basically the third image from the right is after super resolution, and this is what the GAN has produced, and it's fairly close to the original image on the very right. And the two on the left are just other examples of other previous super resolution techniques. Another cool application is image-to-image translation. And pretty much this is kind of like style transfer. So taking the style of some images and applying to other images. So on the left here, you have like taking Monet paintings and converting them into photos and vice versa. And just applying different styles and learning the different, I guess, features of images and applying it to new images or other possibilities for GANs. And another cool application, actually an intersection with natural language processing, is basically trying to take a description of a text and converting that into an image. So like here's a few examples of just input sentences. So this is kind of like a mix between like natural language processing, as you want to understand what the text is saying, and then converting that into an image produced by the GAN. Okay, I'll pass it over to Clive.
All right, so we're just going to go over a bit of the machine learning background required to understand GANs. All right, so first, neural networks. A lot of you might have seen this before, since this is an intermediate lesson, I'm told, but we'll just go over it again anyway. So how neural networks work is typically you have your input, which is a bunch of numbers. That list of numbers can represent anything, such as an image. It can be a list of words. It can be basically anything, as long as a fixed sized vector of numbers. And then you take that and then you do several transformations on it. So then you end up with an output. And those transformations each consist of first multiplying it by a matrix. So you can sort of see that as mixing up all the numbers with each other. And then you apply some nonlinear function. So the reason we need a nonlinear function is because if you multiply a matrix and then a matrix and then a matrix again and again and again, that's equivalent to just multiplying by one matrix. So you're not getting any extra complexity there. And so you're sort of mixing everything up and then pushing it through this nonlinear function, mixing it up again, another nonlinear function, and then mixing it up again to get your final result. So that's how neural networks do their computation. And the reason this is so powerful is because it's very simple and it's very computable. And it's also differentiable, but we'll talk about that later. Yes. Next slide. Yeah. So for example, again, we have the input. This is just a list of numbers. So it's a list of pixel values in the image from, I guess, the top corner to the bottom corner. And then the output is also a list of numbers. So it actually outputs 10 numbers, and each of those numbers represents how much it thinks it's a 0 or a 1 or 2, all the way up to the number 9. And then so you're giving it all these examples of input and output. And the idea is that if you give it enough of these and your neural network is complex enough, it'll be able to learn what any new input that hasn't seen before should correspond to. So in this case, the bottom input that is not identified yet is of course a 5. And it should be able to recognize that if it's trained on enough examples. Yeah, next slide. All right. And then so convolutional neural networks are sort of the key to why neural networks work so well on images. Because if you train a regular neural network connecting every single pixel, looking at every single pixel individually, you get an incredibly large neural network. You get millions of parameters, millions of neurons in each layer. And so you get something that's computationally infeasible, but also it becomes very hard to train because you have so many of these parameters. You have to give it so many examples for it to even figure out what to, how to train. Whereas here, we have something clever called a convolution layer. And the way this works is it repeats the same processing on every k by k square. So in this case, we see there's a 3 by 3 square on this 4 by 4 total image. And you just repeat that same module over the entire image. And the reason this works is because images have a lot of repetitive features. Like if you see a 3 by 3 square, you might see like a dot in the middle and then nothing outside. Or maybe you'll see an edge, just like a line going from one corner to the other. Or you'll see a corner. And there's very simple patterns that are very repetitive over the course of an image. So you'll see a lot of these and it'll be able to essentially summarize what it saw in that section of the image. And then you shrink the image a little bit and then you apply that again. And then so what you're doing then is now you're collecting the information about whether it's a edge or a corner, and then mixing that all together into, now you can recognize shapes in the next layer. And then when you combine all the information about shapes, now you can start recognizing objects, and then you can start recognizing like entire scenes of objects. Says my internet connection is unstable. Is everyone still hearing me?
Yeah, we can hear you.
Okay, cool. All right. So where was I? Building out the representational complexity. Yes. So we have several layers of this convolutions, and it's building up in complexity over the course of all these layers of the neural network. And this is very similar to how the human visual cortex works, actually. So you have these initial neurons that do these edge detection things or these corner detection things, and then they build up into more and more complex structures as you go deeper into the visual cortex. Yeah, and so we have something else called a transposed convolution layer. It does exactly what it sounds like. It just does the opposite of convolution. And it just builds back up from a classification into an image. So that's, of course, what we need for a generative adversarial network. It's going to be able to generate an image from random data. But Kelvin will be explaining that, right? Is that the next slide?
Yes.
Yes.
Okay, so I guess I'll dive into how GANs work. Clive introduced some of the basic building blocks of ML for us to understand how GANs work. But I think before we jump into the technical details about GANs, I'll first go over a quick analogy. So This analogy was actually explained to me when I first learned GANs, and I think it captures the idea of GANs quite nicely. And I think it's good to just go over real quick at the beginning, just so you guys can understand the main idea behind GANs. So essentially what GANs are trying, okay, sorry. There's a question in chat saying GANs, which stands for Generative Adversarial Networks, which is, I guess, introduced at the very beginning. Sorry, yeah, so basically GANs, as my analogy, are trying to print money. So if we wanted to try to do this right off the bat, we would basically get some paper, feed it into a printer, print some money, and then have our printed money. But I guess this is like right off the bat, this is probably not good enough. The money you print just right off the bat isn't close enough to real money, and you'll probably get caught and go to jail or whatever. So instead, we might want to invest in a microscope. And pretty much with this microscope, we can take in real money and fake money and pretty much learn the differences between what's our printed money and the actual money. So basically we can use this information and then make our printer better at printing out this fake money. And that's pretty much it. This microscope and this printer forms the GAN. Just for some more context. So here, the paper as input to the printer is the random noise, which we'll get into. The generator, so basically the GAN consists of a generator model and a discriminator model. The generator model is this printer right here, and the discriminator model is the microscope. So we feed the random noise or the paper into the generator model, and then it prints out our fake money or our predicted data or our fake images. And we also have some real images that we want to learn from the training data, and we also feed that into the discriminator. So we feed in the real training data as well as our fake generated data. We feed these both into the discriminator, and then the discriminator learns to try and tell them apart. And the generator here is learning to try to generate as close as images as to the training data. So we were trying to learn these two models in conjunction. So yeah, so this is the analogy, and this is the structure of GANs you would probably find if you Googled GANs on Google. And I think this kind of looks pretty similar to that analogy. So we have an input noise vector. Because we want to generate different images every time with our generator, we want to feed it a different noise vector. We feed that in as input to our generator network, produce our fake images. We take in our real images as well to our discriminator network. And then the discriminator network will produce some predicted labels, which we will use to basically train these models. So basically, you can think of GANs as like a zero-sum game between these two models, between this generator and this discriminator, because this generator is trying to produce images to try and fool this discriminator and trying to fool it as being as close to the real images as possible, while the discriminator is trying to do the opposite and trying to distinguish the real images from the fake images. So as we train this GAN over time, this discriminator will get better at distinguishing real from fake images, while the generator gets better at producing images that look more like the real images. And basically this generator is basically what the GAN will do, and we can produce new images once this whole network is trained. So just a warning, there's going to be some math up ahead, but we've tried to tone it down to make it easy for you guys to understand. So we're just going to define X as our set of images. So basically we can define the discriminator and the generator as two functions. The discriminator being a function that takes in an image and produce a prediction between 0 and 1. 0 being we think this is a fake image, and 1 being we think this is a real image. While the generator kind of does the opposite. It takes in the noise vector. So Z is basically just any noise vector, and it produces an image. And usually we want this generator and this discriminator to be convolutional neural networks, as Clive mentioned earlier. And so this discriminator network would be composed of the convolutional layers, while the generator would be composed of the transpose convolutional layer. So the discriminator wants to take an image and break it down into a number, a classification of how real or fake this image is, while the generator takes a input noise vector and tries to upsample it into an image. So we'll move on to the loss function. So if
Before
you guys
we move on, actually, does anyone have any questions? Does the bottleneck typically lie in the discriminator or the generator?
Do you want to answer that? Or
So GANs don't use bottlenecks, I don't think.
I think he's just asking about like where the bottleneck for training
Or
occurs. So I
oh,
guess
I guess the point of I guess the idea is to train them both in lockstep. So you typically train one step with the discriminator and then one step of the generator, and you just need to tune them so that they are roughly as powerful as each other. And there can be lots of problems if the discriminator is much stronger or the generator is much stronger.
so. We'll actually get into some, I guess, difficulties of training GANs a bit later, if you stick around.
Yeah.
So, okay, let's get back to the loss function.
Yes.
So if you've done ML before, you've probably heard of this binary cross entropy loss function. And essentially what it's just doing is basically trying to compare two values and seeing how similar they are. Basically, if you look at this kind of complicated equation, this first yi here is the actual value, and the second y hat I is the predicted value. And we pretty much want to see how close these two values are. So if they're really close, then our loss is very low. If they're really far apart, then their loss is very high. And that's exactly what we want our loss function to do. So if you actually, since we're doing binary cross entropy, this this first yi value here is usually a 0 or a 1, being either a fake image or a real image. So if you actually break it down, so let's say yi is equal to 0, then this first term disappears because there's a 0 here. So we're only left with the second term here. And that basically corresponds to this black curve here on the graph, which means that if the real value is a 0, then our second value, if it's close to 0, our loss will be low, while if it's closer to 1, then our loss will be high. And the same thing for if y is equal to 1, it'll be the red curve here. And that's how this loss function is defined. And we'll be using this loss function today in our notebook. Just to jump into the actual loss function that we're using for training. So basically, we have two different loss functions for our two models, our discriminator and our generator. The first one we'll talk about is for the discriminator. So there's pretty much this loss function here is composed of two separate terms. The first term accounts for the real images that's fed to the discriminator, and the second term here accounts for the fake images produced by the generator. So for this first term here, if we kind of break it down, so D is our discriminator, and X here is our real data, so our real images. So our discriminator takes in a real image and it produces an estimate between 0 and 1 of how real or fake it thinks the image is. And basically by setting this binary cross entropy to be comparing 1 against it, it means we want this discriminator to make these predictions closer to 1, since these are the actual images. We want this discriminator to predict 1. So if you think about it, if the discriminator predicted 1 here, then our cross entropy would be very low and our whole loss would be low. Whereas if our discriminator was wrong and predicted 0, then this cross entropy would be very high and then our loss would be high as well. But for the fake images, we want to do the opposite. So the fake images here, Z here being the random noise as input to the generator. So G of ZJ is actually the fake image that the generator produces. We feed that fake image into the discriminator here. And basically, we want to compare this against 0 instead of 1, because basically, we want the discriminator to learn that this should be 0. So then loss here will be low if this is close to 0, and loss will be high if it's close to 1. So this is the loss for the discriminator. I hope it's not too scary and complicated. The loss for the generator also depends on binary cross entropy, but it's a bit more simple. And all it's doing here is saying that it's doing the opposite of the discriminator. It wants the output of the discriminator to be closer to 1 from the generated images to kind of just like fool the discriminator. Okay, so that was a bit of math. You might be asking, what's the point of having all that math? So basically we need that math to learn how our model is able to learn. And basically we use these loss functions during backpropagation so that our model can learn and update its parameters. So actually backpropagation is a different set of math and kind of out of the scope of this workshop. But if you want to learn more about backpropagation, there's a lot of online tutorials about how it works. And it kind of, I guess to summarize it, it uses partial differentiation to minimize a loss function, because a loss function is basically telling us how incorrect our generator and discriminator models are. And we want to minimize that over time. So we use backpropagation to fix our model and make it so that our loss function goes down over time. And basically in TensorFlow, you can use this library, this module called gradient tape to perform backpropagation. We'll go into that a bit more detail later in the notebook. But basically, one algorithm or pseudocode kind of to train GANs is basically we first run the forward pass of the generator and then the forward passes of the discriminator. So basically we want to take in random noise and produce a fake image. We also want to take in a real image. And then we feed these both to the discriminator, so the forward pass of the discriminator here. And then we want to compute the losses using the equations I just explained. We also want to compute the gradients. These gradients will be useful in backpropagation and updating the models of the generator and the discriminator. And we kind of want to just keep repeating this process over and over again until our losses go down over time and our models get better at doing what they're supposed to do over time. So yeah, so quickly I'll talk about Google Colab, which is where the notebook is hosted. If you've used Python before, you might know, have used Jupyter Notebooks before. So Google Colab is actually a nice online tool that's basically a collaborative Jupyter Notebook. And basically, if you've never used Jupyter Notebooks before, they're basically an interface where you can interchange both Python code and real text and like other, I guess, images and whatever. So it's a very nice way to like kind of like lay out your text and explain it, lay out your code and explain it using text. But I guess the nice part about Colab is that you can do it collaboratively with people. And probably the best part about Colab is that you have free access to a GPU or a TPU. And since ML these days, you probably need a GPU and TPU, and those are pretty expensive to own yourself. You have free access on Colab to just use a GPU to train your models. I guess if you're going to use Colab, one thing to note is that there are some resource and usage limitations with Colab. Just be wary of that. One of them is I think is like you can't run your model for like over 8 or 10 hours. But yeah, other than that, Google Colab is a very nice tool for you to get started if you're learning about ML and just trying to like get something started.
All right.
So
any questions at this point? So just to recap, we have convolutional nets which are very efficient at images. We have a discriminator, which is trying to decide whether an image is real or fake. We have a generator, which gets, I guess, rewarded for fooling the discriminator. And so since the generator and discriminator are working against each other, it's called an adversarial network.
correct.
Yeah, all the math is reasonable for everyone. TensorFlow also takes care of a lot of the math. All right, let's go then.
Okay, so we will jump into the notebook. So I think we linked this at the beginning, and I think in an email you might have gotten a link to this notebook.
Yes.
But we will go over it right now.
Yes. So everyone should open this up on their own computers if they can. Just again, bit.ly tech plus GAN. What's it called again?
Let me see. bit.ly/tech plus.
Yes, tech plus GAN notebook.
Yeah. Okay, so I see some questions in the Zoom chat about the loss function. So I kind of tried to avoid explaining what it's used for, but basically we want to use this loss function in backpropagation to update our parameters. So during backpropagation, you'll be taking the partial derivatives of this loss function that we've defined and using these gradients to train and update the model weights. A bit out of the scope of this presentation, but that's kind of like the high level gist of it.
Yeah, like the neural network has like weights in it, and the whole point of training a neural network is you want to change those weights to do what you want. Um, so you end up like if you combine everything together and you want to get like one number for how good your thing is doing, then you can use this loss function as a number for that. So the loss function for the generator this basically says how bad is the generator. The loss function for the discriminator basically says how bad is the discriminator. And since you have one number, and you're trying to tweak all these parameters, the sort of magic of the neural network mathematically is that the neural network is differentiable with respect to all of those parameters. So what you can do is you can take the gradient of that output number, and then you can take a tiny little step to make that output number decrease, to make the loss decrease, just by tweaking all of the tiny little weights all throughout the network a tiny little bit. And in that way, you slowly step towards a better and better solution for your generator or your discriminator.
I think we can move on to the notebook.
Does everyone have the notebook open? Any tech problems happening? Sometimes Colab is a little bit finicky. All right, everyone looks good. All right, let's start then. I guess I'll just look at your screen actually. That might be easier. All right, so we already ran over most of these things, but yeah, so this tutorial is just going to be using a DC GAN, exactly what we said, a deep convolutional generative adversarial network, and uses TensorFlow. So we have, yep, exactly this, generator and discriminator, in this case, the artist and the art critic. And let's see, so we can keep scrolling a bit actually, because we've already pretty much gone over this. It's just another different analogy. So the discriminator and the generator will both gradually get better. Yeah, and so this animation here is actually really cool. I don't know if it's playing because my internet is bad. Yes. So you can see that initially starts as this random sort of noisy grid, and then it sort of resolves into a recognizable image. And that's typically what happens with GANs, is that the generator and the discriminator both gradually get better over time. So you'll see better and better images over time. All right, let's go. So the way you can run this Python code is you can press the little play button to the left of this cell, or you can press, what was it, Control Enter while you have the cell selected.
Yeah, I think so.
Yeah. So if you just run that, it'll not output anything. That's fine. If you press play on tf.version, you should get something like 2.3.0. So TensorFlow version 2.3. Install some stuff. So just keep pressing play on these first four. These are just like installing all the stuff you need. All right. Now, so we're going to use the MNIST data set. So if you saw those, if you don't remember those handwritten digits from earlier, that's a very large data set from the, I don't know what MNIST stands for, but like it's some large organization that has data sets. And this is one of the main data sets that people use to learn machine learning is the MNIST digit, handwritten digit data set. So what you're going to do is just load the data, very simple, tf.curious.mnist.datasets.mnist.load data. And what it's going to do is you're going to get all the training images and all the training labels as two separate lists. All the training images are, of course, the images as like, I think it's 26 by 26 images, and the labels are from 0 to 9. Just press play on those. Like there's some, like, you usually have to do a bunch of data cleaning to get stuff to be usable for a neural network. So for example, getting all the images to be between -1 and 1, instead of normally on a image, you're between 0 and 255 on each pixel. Buffer size, batch size, batch and shuffle the data. Yeah. That's also a little bit out of scope, but it just separates all the data into batches of size, in this case 256, and it trains all 256 at a time. All right, so now we're creating the models. This is where we have to remember the diagram from before, where we have a bunch of layers stacked on top of each other. So first, we're looking at the generator model. We start with, the model is a sequential model, tf.curious.sequential, and you're just going to add a whole bunch of layers to it. So what these layers do is you're starting from a noise vector, which is of size 100. So you just have random numbers, 100, and you're trying to expand that outward into an image. So you start with 100. You have batch normalization and leaky ReLU. Ignore those. It's okay. Those just help the training be a little bit more stable. And then you reshape that into, you have a dense neural network that is of size 7 times 7 times 256. So imagine in the original image of the layers of the neural network, you have 100 neurons up here, and they're all connected to each other. And then there's 7 times 7 times 256, which is some large number. And that is how many output neurons there are. So we have these output numbers, and then you run it through convolutional layers a few times to scale it up into a larger and larger size. So you're going from 7 by 7 to 7 by 7 to 14 by 14 to 28 by 28.
Sorry, these are transposed convolutional layers.
Yes. Yeah, you can look at all of these different layer types on your own time. But yeah, batch normalization and leaky ReLU are some very common ways to make neural networks train a little bit better. All right, then next we have now our generator model. So we have now this model that is just a neural network with this number of parameters and neurons. And so the generator doesn't have any training. So all it is very random weights. So it doesn't really do anything in particular right now. So if you decide to generate an image with this cell here, you're just going to get a random image, which is pretty much as expected. Yeah. So next, the discriminator. You're using convolutional layers. So you take the image size, input shape 28, 28, 1, and then you're squeezing it down to 5 by 5, and then having another layer of convolution on top of that, and then finally getting it down to a single number. So that last line, layers.dense1, is the output. And so it outputs a single number. And what we're going to do with that number is we're going to treat it as, if it's a 0, then which one? Yeah,
Fake,
if it's positive, it's real. If it's negative, it's fake. Yeah. And so now we've tried to use the discriminator on this random image. Of course, the discriminator has no idea what to do. It's been randomly initialized as well. So its score is close to 0. It's slightly negative, so it thinks it might be slightly fake, but like it has no idea because it hasn't been trained. All right, now define the loss and optimizers. That's you now, Kelvin.
Okay, I'll take it over. Okay, so basically, we've now just set up our two models. Clive will help you walk you through that. So now we want to define the loss functions and the optimizers, and these will help us actually train the model and update the weights. Because right now, when you run the model, these are kind of like, they don't really do what we want it to do. We want to train it over time so that later on, it will actually produce images and actually distinguish real from fake images. So as we explained earlier, our loss function here you'll be using binary cross entropy. So we run that, define the cross entropy module. And then basically, if you remember the discriminator loss from earlier, it was basically two terms being summed together. And this is exactly what we see right here. Here is the real loss and the fake loss. So real loss being taking in the real images from our training data and comparing it to ones. Whereas the fake, the second line here is the fake loss. So we take in the fake images that our generator has produced, and we want to compare that to 0. And these are exactly the cross entropy formula we saw earlier. We add them together, and that's our whole discriminator loss. Similarly, the generator loss is also what we saw previously. We take in the fake output. So this is what the discriminator thinks of the fake image. We want that to be as close to 1 as possible. So our generator is able to fool the discriminator. Also, we saw this equation earlier. And basically, using these two loss functions, we'll be able to backpropagate and train our model. So here we've defined two atom optimizers, one for each model. I think someone asked about SGD in chat earlier. These are just different optimizers that are, in my opinion, easier to use, especially if you're just starting out. But SGD could be used here instead of atom as an optimizer. So yeah, we set up these optimizers here. We also want to just save checkpoints because Colab sometimes times out if you don't watch it for long enough. So we don't want to lose if we're in the middle of training and then it times out, we don't want to lose all of our progress. We wanted to kind of save checkpoints over time. We just want to set that up right now. So later, every few iterations, we want to basically output a checkpoint of our model. So then if it does get interrupted, we can just start training from the checkpoint instead of from scratch. And now we will define the training loop. So this is basically the loop that we
There's a question actually.
Okay.
Yes, it's the learning rate. So 1e-4 is the learning rate in Atom, which is essentially when you have the gradient, which gives you the direction and how much you need to change each of the many parameters within the neural network to get slightly closer to a better answer. And so 1e-4 just tells you like only take 1/10,000th of a step. And so the smaller that number is, the slower it trains because it takes longer to actually step towards the correct answer. But also, if you take 2 big steps, then you'll start going way off whack, and it will start not being able to go in the right direction at all. So you need to find a fine balance, and usually 1e-4, somewhere around there, is a good number. All these are like very empirical. You just try things out until they work.
Yeah, you want to just like try different values and see which has the best performance on your model. So the good thing about Atom is that it will actually kind of adapt itself over time. It's kind of where the ADA in Atom comes from. So then you don't have to tune that many parameters. I think this 1e-4 is just like the initial learning rate or something like that. But basically it'll over time adapt itself to the factor you want. If you use SGD, you'll have to tune that out yourself, which is, in my opinion, more work. So yeah, that's what this parameter does here.
ADAM stands for adaptive moment estimation, if anyone wants to look that up. Right. So is this me or you?
Oh, this is me. Okay, so this is the training step for our model. And I guess essentially, if you remember from the slide before, we want to first here, we want to do one first forward pass of our generator. So basically we want to start with some noise and pass that to our generator. So our generator tries to produce one kind of fake image. And then we want to use this fake generated image and give it to the discriminator, and also give the discriminator some real images. So that these are basically the forward passes of the discriminator. And using these outputs, we want to use them in our loss function and calculate the loss, and also use these basically to calculate the gradients in backpropagation to update our model. So if you remember earlier, these are the two forward passes, and then we want to calculate the losses and their gradients here. And then in this last step down here, we want to basically apply these gradients onto our model and update all the parameters in our model. So basically TensorFlow, this gradient tape here, at a very high level, what it does is it basically keeps track of a lot of the computed values when you did your forward pass here in calculating the loss, so that it knows how to calculate the gradient. Because if you think about it, calculating the derivative in a computer is pretty difficult. But basically, with this gradient tape, TensorFlow keeps track of what you use to calculate the forward pass, and it will basically calculate the gradient in reverse when you call this right here. That's kind of like a high-level explanation of gradient tape. You can read into TensorFlow's documentation for more details about that. But yeah, so basically this function here performs one single step of training our model. And basically we want to keep repeating this over and over again until our models learn and become better at producing fake images and also classifying between fake and real images. So here's our main kind of train function. Well, shall I run these? Let me just run these. Run these cells. Okay, so this is our main training function here. I won't go over all of it, but basically you want to set the number of epochs of training, and then it'll train for that long, and it'll basically go through all the images in the data set and perform the training step above here. And after every epoch, I think after 15, it'll save a checkpoint. We define that right here. And it'll also save images, which we'll get to later. Yeah, so we're gonna just let it train here. Wait, sorry, this is just the definition of the function. Training is down here. Okay. And I think this train function also calls this generate and save images function, which takes in one test input, so one testing random noise input, and pretty much generate with that. And it'll also print that out for us, which we can see in a bit. So let's just run the training. This will call the training function and start training our model. So essentially what we've been doing here is basically we have one input seed here. And this we use so that we can see the progress of our model over time. So we have this one fixed seed that after every epoch, we'll use this input seed and generate an image and see how the image will improve over time as we train after every epoch. So it shouldn't take too long with the GPU, I think. So we've already trained 2 epochs. And right now, since we're just starting off the training, these don't really look like good images. They're all like very blurry, while the model still learns to generate these images, and also the discriminator learns to differentiate the images, since they both depend on each other. And if you just keep this running for a while, I think after like 40 or 50 epochs, you'll be able to see like generated images here, and then it'll start looking like the actual images from the data set. And I think, yeah, that's about it. That's what the GAN has been like set up and designed to do. So once we think we've trained enough epochs, we stop, we save the checkpoint, and then we basically use that generator from the checkpoint and produce new images. So I think these final blocks of code here basically just takes the images that are being generated out right here and turning them into a GIF so that you can see the progress over time, kind of like the GIF at the very top of this notebook. This GIF right here. Yeah, so we want, after you run the code at the very end, after it's done training, we'll be able to generate this GIF and see how these images get better over time. Do you have anything else to add, Clive?
No, not really. You can already see sort of that it's trying to make it look like a number, but doesn't really know what a number looks like yet. But you can already see there's like distinct lines, there's sort of curves. And then eventually you'll start figuring out what's actually a number and what's not.
If anyone has any questions, feel free to drop them in the Zoom chat below.
Has everyone been able to run this? Is anyone having any like errors or questions with that? It should all be taking about 12 seconds. So if it's taking much longer than 12 seconds, might need to change a couple of settings as well.
So there's a possibility that you're not connected to a GPU, because I don't know if Google Colab will automatically give you a GPU. If you're not connected to a GPU, you can check that by going here to runtime, change the runtime type, and just make sure you're on a GPU.
Right. All right, so shall we go back to the presentation then?
Yep.
Any other questions about anything we've gone over so far?
So we can come back to this notebook afterwards and
So
then
basically,
see.
we're just going to talk about ways you can extend this, and then you guys will have about an hour to just go and play with it in whatever way you want. Whether it's this notebook, just tweaking things within this. Yeah. I think my connection is really bad. I'm sorry.
We can still hear you. Oh no, I think we're losing Clive. Okay, we'll wait for Clive to come back, since the next slides he will go over. But in the meantime, again, if you have any questions, feel free to drop them below. This is meant to be more like a interactive, you try things out and we can try to help you with it. I guess in the meantime, someone asked a question earlier for me to go over the loss function again. I can do that while Clive fixes his internet problems. Let's go back to the loss function. Okay, so binary cross entropy, this is a general. Sorry, Clive, we're just gonna go over the loss function real quick, and then you can continue. Someone asked about going over the loss function.
Oh, okay. Cool.
Okay, so I see the question as why do we use binary cross entropy? There's actually, you can kind of choose any loss function you want to, and as long as it's maximizing the values when they're close, minimizing the values when they're close and maximizing the value when they're far apart, you can actually use any loss function you want. Binary cross entropy is just used a lot because it's easy to take the derivative of, if I remember correctly. But yeah, other extensions of GANs, they will use different loss functions, and you'll see that they will have different performance as well. Okay, I guess we can just, since Clive is back, we can jump back to the extensions.
Yeah. All right. Yeah, binary cross entropy has some nice properties specifically for classifications, but like it's, I feel like most loss functions should work roughly similarly. Yeah, it just tends to be slightly better at classification problems. But yeah, besides that, we're just going to go over some extensions. And then, yeah, then we'll let everyone go wild with the Colab notebook or with whatever extension projects you want. So some things you can try out. Can you still hear me, by the way?
Yep.
Okay, awesome. Okay, so you can try, just like on the current notebook, you can actually just try tweaking some of the parameters, like adding more layers, removing some layers, changing the sizes, and seeing like how that changes, how well the neural network trains. And so that's one way of doing things. You can also use different data sets. So SciFar is a really, really low resolution object data set, and you can use those images to try to create an object classifier. You have SLEB-A, which is a very large data set of very high resolution celebrity images. And you can also just get any set of images you want. So paintings, I have a project using Twitch emotes, anime characters, anything like that. You can also try
Wait, sorry, I think we're
so
losing you, Clive.
CycleGAN is, actually there might be a demo of CycleGAN in the TensorFlow repository.
I think you cut out for a bit there, talking about the
Man.
model extensions.
Oh yeah, yeah. Can you hear me now?
Yeah, we can hear you now.
Okay. So yeah, the model extensions, you can try out different models, and there's a lot of different models that are in the TensorFlow repository as demos, as demo notebooks, such as this one that we've just showed you, which is actually directly from the TensorFlow repository as well. So you can try those out. You can also try to build it yourself. I don't advise that. That's very difficult. But yeah, CycleGAN is a very popular one where you can generate analogies of images. So if you have pictures of horses and corresponding pictures of zebras or something like that, you can like translate horses to zebras in any image you have. StyleGAN is a really, really high resolution face image generator. So it's trained on Celeb-A, I think, and you can, it's very, very good. It's incredibly realistic. Yeah, and just play with some of those online implementations if you want, or just pretty much anything. Yeah. That is a list of project ideas, and feel free to go for anything. Oh yeah, we want to talk a little bit about why GANs are hard. So there's a few challenges here. So it seemed very easy going so far. Like back in, I think it was 2014 or something, Ian Goodfellow published the first paper on generative adversarial nets, and no one was able to replicate any of the results in his paper for like a year, which tells you how hard it is to actually get it right. So there's a lot of interesting problems that can arise if you don't have quite the right parameters, such as mode collapse. Mode collapse comes from the fact that there's no real incentive for diversity of generated images. All you're really doing is getting the discriminator to distinguish individual generator images from individual training set images. So you don't really know whether the generator is generating anything different. So it can actually just output the same image no matter what, and the discriminator won't be able to tell. So there are some alternative loss functions. You can actually take multiple images into account. You have some explicit diversity incentives, stuff like that. Another problem is vanishing gradients. So if the discriminator becomes too good, the generated images are always marked as fake. And so the generator isn't actually able to learn anything because all of its images are marked as fake. And so it's not able to get any feedback on how well it's doing. And so you need to make sure that the discriminator doesn't become overwhelmingly good. So you can use alternative loss functions. You can actually step the generator multiple times for each single step of the discriminator, normalization, stuff like that. And finally, GANs as a whole, they have this problem of non-convergence where the discriminator and generator are sort of following each other. And if you imagine like two things orbiting each other, if they're constantly trying to reach each other, they can overshoot and overshoot more and more until like things completely diverge from each other. So you need to be able to sort of dampen that oscillation around each other. And so they spiral in towards the right answer. So there's a bunch of different methods to do this. There's what's called gradient penalties. You can look up, there's a whole bunch of papers with gradient penalties. Instance noise is also another interesting idea. It's been used to combat that. And generally speaking, GANs are more solved now. Like people generally know and understand how to train GANs, but it still can be pretty challenging if you're writing it from scratch. All right. Further readings. Yes, another thing you can do in the next hour is read these and ask questions, because these are actually really, really good articles that can teach you a lot if you like spend the time to dig in and understand them. Yeah, so WGAN is a architecture that solves most of the problems that were listed on the previous slide. DistillPub in general is a really, really good publication, but specifically this article is talking about what open questions there are about GANs. And this Medium article talks about why it's so hard to train GANs. Pretty much similar to the examples that I just listed in the previous slide, but goes over it in more detail. Yeah. So that's that. So there's a request to go over the Twitch GAN project.
Sure.
Maybe
We can do that.
Yeah, we can do that. So if you just go to, if you just click on that, it's just at cchan/twitchgan. All I did was I downloaded like, 4 million or so Twitch emotes from Twitch and tried to train it on Colab, and it didn't do that well, but it was okay. So you see epoch 2 and then all the way up to epoch 41. You can kind of see something happening there. Like the 41 in particular looks like a Pokemon, but yeah, that's quite an old project. I might revisit it now, but that is an example of what kinds of things you can do with GANs. So with this one, I explored specifically DC GAN at first. DC GAN is sort of hard to get training correctly due to those 3 problems that we had before. So based on that blog post about from GAN to WGAN, I changed it to a WGAN, which stands for Wasserstein GAN, and it trained a lot more stably, and it actually outputted things that looked plausibly like Twitch emotes. Yeah. So with that as an example of what things you can do right now, I guess we'll let everyone just do whatever. And we'll be around to answer any questions and chat as much as you want for the next hour or so. And also, should we leave contact information if we want to talk to us later. Guess we forgot about that, but
Oh yeah, we should.
I
We
will
can
put
just-
my contact info in the chat,
Okay.
I guess, if you want to ever get in touch. That's my email. Whoops, wrong chat. There. All right. Yeah. And that's that. That is the end of the formal presentation. Thanks, everyone.
I'm gonna go back to my notebook and see how the model is doing.
Okay. Let's see. Is it looking realistic?
Okay, I think this is the last epoch.
Oh, okay. It actually looks really good.
Yeah, so most of these, with a
Look
few
number-ish.
exceptions, look like numbers, yeah. So I'm sure if you train this for more epochs, it would be even better.
Oh yeah. So could you please go back to the list of readings?
Yeah.
Let me just paste the link to the presentation actually, so you can actually reference this entire presentation later on if you want. There we go. That's the link to the presentation, and the list of readings is in there on the second last-ish slide.
Yep.
Thanks everyone for coming.
Yep. Thanks for dropping by tonight.
Question, are CNNs always used, or are there any cases in which you would use a regular network? Generally for images, you want to use CNNs because, again, you have sort of that repetitive structure and you have a lot of pixels. So you want to reuse as much as possible, because the more you reuse, the easier it is to train, because there's less variables to train. But in some cases, like, yeah, like for things that aren't images, for example, if you're generating text or something like that, you might not use convolutional nets because I guess they're not really applicable. Natural language processing is sort of its whole own field that is very separate. So there's also just like general structured data parsing. So if you have a database with a lot of columns and rows, and you want to classify over those, then you would probably use just a regular fully connected neural network. Yeah.
I think some of the extensions for GANs like have like a bit modifications to CNNs, because like I guess vanilla CNNs are like not good enough for their purposes. So sometimes they like modify the architecture a bit so that it produces better faces or images or whatever.
Yeah, there's a lot you can do. Yeah, there's like what, skip connections and dropout and even fancier types of layers beyond convolutional layers. Will there be a recording of today's session? Yes, there is a recording. Does someone from Tech Plus want to comment on where that will be posted? Yep, we will be posting that after this workshop in a few days. Hey.
Yeah, we have it recorded right now, and we're going to be posting it later on, and we'll just send out an email to everyone with the link of it, as well as the slides, if you don't already have that.
Right. Is anyone working on these extension things, and any questions or would like to talk more about any of these? Might actually end a bit early if that is the case. You can always feel free to contact us. Kelvin, I'm copying your email to the last slide.
Sounds good.
All right. It seems like everyone is doing okay here. So we might actually end a bit early and let you guys go. But you can always reach out later if you want to talk about the project that you're working on, and or ask any questions or ask for ideas or anything like that.
Or you could just reach out, just ask about general things. I'm sure Clive will be able to answer any of his questions about his experiences. I can ask anything. You can ask me about anything about my experiences. We should be open to that too.
Couldn't hear most of that. Right?
Oh, I was just saying that they can pretty much just feel free to like reach out and ask us any questions about like any of our previous experiences.
Yes, that too. Feel free to do that. All right. I guess that's it then. Cool. Thanks everyone for coming. Good night, everyone. Thanks everyone for coming. It's been a good time.